So let us continue with the discussion of the atomic mechanism of the growth. As you have seen in the last lecture, we can actually use flux balance across the solid liquid interface to get growth rate. So let us now simplify the equation. As you know, we can always assume, basically assume means what? We can always consider that the number of atoms in the liquid can be equal to number of atoms in the solid. At any time it is possible, but it is an assumption. Let us assume this is equal to n. Again, we can also think that, as we have done already, mu L is equal to mu S is equal to mu. I have already done that. Basically, I have already taken this as a mu S, mu L equal. So we can do that. Okay, if you don't do it, it will become like that. But this assumption is correct because frequencies of the atomic vibration will not vary much. Second, so now question is that if I have a diffuse interface, the one which I just now discussed, diffuse interface will have a large number of sites in which atoms can easily grow, go and sit. So therefore, in a diffuse interface, the F alpha will be quite large. And here one can also assume that FL is nothing but fraction of the atoms which are able to successfully jump is in the liquid can be 1 because it has higher energy, temperature is the liquid is higher, vibration frequency is also their number of times they are able to make jumps is also higher. So therefore FL can be 1. So if I then write down delta J can be equal to exponential minus delta GT star by KT multiplied by these factors will come out. So as you know, NL is equal to N then, so I can write down here N mu L will become mu, okay, and then what I got back, NL mu L goes out, so FL I have already considered 1, it can be, then it's become F alpha exponential minus delta G solid to liquid. This equation becomes very simple. We can always consider this as a constant A because number of atoms, frequency, they are constant at fixed temperature. This barrier height is also fixed temperature, it will be constant, or we can let us suppose this is a constant term, then it's become 1 minus F alpha exponential minus delta G solid to liquid divided by KT. Now let us apply this equation for different types of interfaces. First interface we will consider as a diffuse, the one I told you. Diffuse means in a case of a diffuse interface you have a large number of sites available for the atoms to go and sit. So therefore in those cases we can always assume F alpha to be equal to 1 in these cases. As you see here, why its F alpha is to be 1? Because you have basically it's not will be 1 but it will be very high, fraction will be close to close to 1 because you have a large number of sites available to the for it to go and sit there. So you can make these assumptions. For a diffuse interface F alpha can be 1. So therefore for the diffuse interface the flux balance which is equal to growth rate is basically A 1 minus exponential minus delta G solid to liquid by KT. That's what it is, and this is an exponential function, okay. So therefore we can clearly see the growth on a diffuse interface will be exponentially increased as a function of temperature or as a function of undercooling. As you increase the undercooling, you are basically decreasing the temperature. So that means what? The main driving force for this growth or whatever, nucleation growth, everything is basically coming from the undercooling that we discussed in the last lecture. So therefore, more I increase the undercooling, more is the growth rate. because this 1 minus exponential. So therefore this factor will become smaller. As you see here, the t will increase, this factor is become smaller. So 1 minus of these will increase, and the a is a constant term, therefore growth will increase. So as you can clearly see that for a diffuse interface, such a simplified expression people are using all throughout. In fact, one can actually use much simplified expression. I can actually expand this term and get a better term what the mechanical engineers use. So you know exponential minus x is nothing but 1 minus x plus x squared by 2 goes on. So if I truncate here, if I truncate there, if I say higher terms are not of any importance to us, then I can write down 1 plus this term delta G solid to liquid by KT, and then it's become A, because 1 gets cancelled, multiplied by delta G solid to liquid KT. Okay, and as you know, so therefore I'll get back here. I'll move it here because you cannot see it. And now what actually you get? Let's see what actually you get there. So you get the growth rate is equal to the flux difference is equal to A delta G solid to liquid by KT. And what is delta G solid to liquid? We know that delta G solid to liquid transformation can be converted to latent heat delta T by Tm. Okay, so therefore I can write down this is basically proportional to latent heat delta T KT Tm. So that means what? The growth rate is directly proportional to the undercooling. And this kind of growth is known as continuous growth in the literature, where atoms will keep on jumping and attaching to the thick solid surface. From the liquid they will jump, attach directly to the solid, and they are higher than undercooling, higher is the velocity. This is only possible in pure metals normally. Let me tell you, pure metals are few pure ceramic solids, where in ceramic solid each molecule can easily jump as a object, as basically entity, and attach to the solid. So as you can see here, after making so much assumptions, the theory actually boils down to very simplified equations where you can do that. But you know, the moment we think of this kind of interfaces, diffuse interfaces, such kind of continuous growth mechanism is possible. But if I change the interface, from this diffuse or smooth interface to the jagged one, which I've shown you in the last slides, like silicon or in case of germanium, this assumption will not be true, many of these assumptions. So what will happen there? Okay, let us see what other things can happen atomistically, then we will go back to the mathematical equations. That's what we will see. Well, let us suppose, this is again taken from Porter and Stirling, if I have a solid and a liquid, I interface very kind of a flat. So if as the interface is flat, so therefore if the atom from the liquid jump and sits on the surface of the solid, it will only satisfy one bond. Suppose this cube is basically considered to be as atom, and if is all bonds to be satisfied, then all the 6 sides must be attaching with some other things, right? Only here you see here it is only getting attached to this one surface, the bottom one, and rest all surfaces are basically hanging. So therefore the atom, even it comes from a liquid, it will not feel completely comfortable, because in the liquid it might have all the bonds are not satisfied. In the solid, when it comes, only one bond is satisfied. So that's not much difference between these two situations as far as energetics is concerned. So it will rather try, because solid is considered to be order atomic arrangements it has, so it will try to, atom will try to satisfy as many as bond possible. So in such a situation, how the solid will grow? Solid grows what is known as by ledge mechanism. What is a ledge? Okay, this solid surface, solid liquid interface will create a ledge. Its ledge is nothing but a step, and these steps are basically, I will come back to it how these steps are created. Steps are basically created by nucleation. So let us first assume that a step is present, okay, then we will come back to how the step can be made. So if I have a step created like on the surface, which is shown as a ledge here, this step actually, now consider the situation here and there. Here actually if the atom sits, it can satisfy at least 2 bonds, if not more. But in the first situation here, atom can satisfy only 1 bond, that is because it is in touch with the bottom surface with the solid. But here it is in touch with bottom and one of the sides, correct? Now better situation will be to create a kink. Okay, as you see here, there is a kink. Kink is nothing but like this. You can create a kink, and this kink they can allow, this is known as a Z, can allow actually the atom to satisfy its 3 bonds. Okay, so if I create many such kinks, and I can actually allow many atoms to come and jump and attach to the surface of the solid. This is exactly what happens in a silicon or in germanium. Okay, so a zog or a kink is more easy to have places where the atoms in the liquid can jump and join. So that means what? In these cases, all the surface is not available for these liquid atoms to come and sit, like in a diffuse interface. In the diffuse interface, we assume F alpha to be equal to F solid or F alpha whatever, it will be alpha is a solid phase is 1, that's no longer valid here. F alpha will be a fraction and it will be very low fraction, let me tell you. So how these ledges or these kind of things can be created? Okay, there are many ways. One is known as surface nucleation. Okay, this is what is shown here. What you can do, an atom can sit here. Okay, as couple of atoms, or maybe not couple, maybe several atoms can sit here and create a nuclei. Okay, it can create a nucleus actually, not nuclei, nucleus on the surface. What it can do basically, instead of one atom coming and sitting on the surface, a bunch of atoms can come and sit. That's much easier, right? If one atom come and sit there, it is only satisfying 1 bond at the bottom of the surface. But if I suppose many atoms are coming, cluster of atoms are coming, you can clearly see this atom has satisfied many bonds. Similarly, this atom can satisfy many bonds, which is energetically more favorable. So therefore, this 2D nucleation basically is more energetically favorable initially to create a step or create a basically ledge. That's what happens. It creates, these kind of ledges are created by surface nucleation. So what does it mean? That means what? That means for such a kind of situations, the growth rate is not like straightforward function like which I shown you. Growth rate is basically depends on surface nucleation plus the attachment of the atoms on these ledges. It is more complex than we can think about it. This happens actually in reality. Okay, and that is one way of doing that. Otherwise, we can do one more thing. We can actually create a screw dislocation on the surface. We can create a screw dislocation on the surface. That's also possible because many of these solid surfaces can have a extra plane coming out, just like a slip happening in a crystal. And better to have a screw dislocations than if you create a screw dislocation. You see there is a screw dislocation here present. And in this screw dislocation, an extra atom coming from the liquid can easily sit there and satisfy many bonds. Correct? But when you do that, the screw dislocation will be, say screw dislocation terminating a solid liquid interface is shown there. You can see this is taken from W.D.T. Reed. Reed is basically a book in dislocation in crystals. Reed is one of the pioneers in dislocations. So addition of atom at the ledge causes it to rotate. What will happen is that very interesting happen. It can actually, as the atom comes and joins, this screw dislocation will rotate. Why it will rotate? Because if the atom comes, it cannot no longer retain its screw nature. It will, as the more and more atoms come, it will slowly lose its screw nature. So to retain its screw nature, it will try to rotate itself. That's what you see here, it is getting rotated. As the more atom comes, this was there, then it is rotated, comes like this. This was there, rotated, comes like this. So screw dislocation is another way of creating a ledge or creating a surface structure where these atoms can actually attach. So one is 2D nucleation, otherwise the screw dislocations. Well, these are the two basic things which people see here. Now I'll simply, today's whatever time I have, 4-5 minutes, I'm going to tell you what actually can happen when I have a surface nucleation. Let us discuss that part. Okay. So as you see that what we need to modify, we need to modify in this expression. This will remain same. This kind of construction will remain in case of that. Only thing is going to change is that this is basically the total energy difference between the solid and liquid of the atoms. This one is going to change. Here it was only simply migration or transport because of that, the barrier. But in this set of situations, it's not only that, you need to have also nucleation barrier, because you need to create either a 2D nucleation zone on which a ledge can be made, or you need to create a dislocation structure. Either of these T will lead to energy, because not dislocation will lead to increase the strain energy of the system, or 2D nucleation will increase the energy of the system also. So let us first consider 2D nucleation case. What will happen if I consider 2D nucleation? So let me erase this part. We will use the nucleation theory again. Let us suppose I have a 2D nucleation picture I have shown you. This is a surface like this between solid and liquid, and you have created something like this. This is just like a cylinder, okay? It's just like a cylinder. Cylinder will have height h, because these steps will have height h, and you can also have radius r. Because a couple of atoms has come and they sit on the surface, so they look like a cylinder. Even though they will spread, but still it is better to have a cylinder. Why? Because if it is like this, then many of the atoms can satisfy bonds, and then you can create another layer like that. So if I assume that it's a cylinder of radius r and height g, then what is this energy? This is nucleation, surface nucleation, okay? Surface nucleation, because of that. So this basically, let us write down volume. Volume is pi r square h multiplied by Phi energy, volume P energy per unit volume. This is minus, obviously, for the nucleation, plus you are creating a surface area twice pi r h, surface area of that, multiplied by the interfacial energy between this solid and that. That's what is basically a very important factor. So that is what is basically the total energy of the surface nucleated force. Okay. Now you can do all mathematics on that. You can actually find out what is the critical size. Critical size A again 2 gamma by delta GV, and delta G star, you are creating a new delta G star, that is surface nucleation. That's what is important aspect for us. That is what we want to know, because we have to add this part with this, because this is already present. Migration things will be there always, but this is an extra term coming into picture in the calculation. So that's nothing but, if you do the proper calculation, it will be pi h r square. R square means r star square basically. So r star square divided by delta G BV. Okay, and therefore, if I have that, now I can write down the rate, because we are calculating the growth rate. So what is the nucleation rate? Nucleation rate equation, if you go back, nucleation rate, N surface nucleation rate is equal to number of atoms present on the surface. Number of atoms mean number of atoms coming there, multiple exponential, and you can also, there will be frequency term coming into picture, exponential minus delta G surface nucleation star by KT. That's the rate. So we need to connect this rate with the growth rate later on, okay, right? That then only we can get into such a kind of flux balance equations. So what we need to do is that we will use this nucleation rate and then bring into the growth rate equation, okay. So that I'll do it in the next lecture and show you how this will give you interesting equations and which can allow you to explain the growth by dislocations or by surface nucleation in these materials. So atomistically, at the end of these two lectures today, or this lecture actually, last one and this one, atomic mechanisms of growth during solidification is very very interesting. It actually not been discovered in one go. Basically it took about 50 years research to understand how this growth happens. Okay, remember I have only talked about two different situations for the faceted interfaces. One is this nucleation on the surface to create a ledge, other one is a dislocation. You can also have a twin situation. You can also, in the case of silicon actually that's happened, you can have a twin re-entering angles. You can actually have twin surface twins present on the surface, and these twins can actually allow the atoms to get attached. And that is what happens in silicon more. And that's why in aluminum silicon alloys, the twinning silicon gets multiple twin, and they have all kinds of features built in on these silicon fibers. So that's also another possibility. So, but we will not have time to discuss each of these cases in detailed manner. These are there in the books. So we can actually have multiple situations of growth in case of faceted interfaces where you have steps on this kind of small steps on these surfaces. So we will keep on discussing all these aspects in the next lecture also.